So last day we were discussing about this. For stretching the spring or compressing the spring, we have to do work, and that work done will be stored as elastic potential energy of the spring. So here you can see when we stretch the spring to a distance x, what happened? Restoring force will come into play. Restoring force. What is restoring force? Opposite to our force, one force will be there. The spring will exert a force. Opposite to our force. Spring will exert a force to bring it back to its original position. This is the original position. To bring it back to the original position. So when we stretch the spring, in rubber band also you might have seen, when we stretch it, it will be in the stretched position. When we release our force, what happens? It returns to its original position. So when we stretch the spring opposite to our force, the spring will exert a force, and that force will always try to bring it to the mean position. Okay. Then similarly, when we compress it, then also that force, restoring force, or the spring force, spring will exert a force to bring it back to the mean position. So suppose we stretch it through a distance x, then that force, not restoring force, is directly proportional to this displacement. When we stretch it more restoring force acts. So the restoring force is directly proportional to displacement. You see that F is proportional to X, and we give negative sign to F, restoring force. Do you know why? Because when we stretch it to the right, that restoring force is trying it to bring it to the mean position. That is opposite to the right. We are stretching it to the right, but restoring force acts to bring it to opposite direction. No. Force is always opposite. Restoring force is always opposite to our force. So always try to bring it to the mean position. Similarly, when it's compress it, then it is opposite to that. Restoring force is opposite to that. It will try to bring it to the mean position. So restoring force, we give the sign minus because it is opposite to displacement. Both are vector quantities, both force and displacement. So F is minus F is proportional to X, or F equal to minus Kx, we can write restoring force. F equal to minus Kx. That graph is plotted here, restoring force and the stretch or compression. You can see it is a straight line graph. So this is what I have explained. The small work done to stretch the spring through a small displacement dx. We understood when we apply force to stretch or compress it, opposite force acts on it. A spring will exert an opposite force which will bring it to the mean position. That is known as restoring force or spring force, and that is directly proportional to displacement. That is what we have seen. Therefore, the small work done in increasing the length of the spring by a small distance dx. Work done, we know what is the formula, F dx. Work done is equal to F dx. So here we have to apply a force opposite to the restoring force. So we write minus of F dx. We write minus of F dx. So minus of F equal to minus Kx into dx. Do you know why we put minus F here? F is restoring force. What is minus F? Minus F is our force. Our force. Minus of negative, opposite to the restoring force, we have to exert force on the spring to stretch it. So minus of F you have to take. So minus of F is already minus Kx, restoring force, into dx, small displacement. So the work done is equal to minus of F dx minus of minus Kx dx, which is equal to Kx dx. We got it. This is the small work done to stretch the spring to a small displacement dx. Then total work done, how will you find total work done? This is a varying force. We are applying we cannot tell we are applying a constant force. We can only tell we are applying this force to stretch it through a displacement x. We are stretching the spring. This is for small displacement. And what is the work done to stretch the spring to have a displacement x? That is what we have to find out. And in order to stretch it, we don't know whether we are applying a constant force or not. So what we have to do, we have to take the step of integration. If sigma, you know sigma. Sigma is for summing, adding. So when sigma 0 to x like that, if you write it, we can add things. But sigma is used when constant force or constant forces are acting on it. But here we cannot tell whether we are applying a constant force or not. In that case, varying force will also be there. In such cases, we have to introduce the idea of integration. Integration also is sum, but the only difference is integration we can do in the case of varying forces. Gravitational force, when we move from surface of the earth to infinity, the force is varying. Electrostatic force, when we move from the charge to a distant place, that electrostatic force is decreasing. So in such cases, we can use this integration. Integration means the sum itself, but when the forces involved are varying forces. So show that step here. And you can see in our textbook, some equations are there on integration. Differentiation we have studied now, just like that. Some equations are there, integration formula, page 64, you can see. Integration formulas are there. So one formula we are applying here, that's why I am showing this. Integral means sum. Integral x raised to n dx. A quantity is having a power n. So this is the integration and dx sign will be there when we put integral x raised to n dx. What is the formula used? The formula is x raised to n plus 1 by n plus 1 power plus 1. X raised to n plus 1 by n plus 1. If it is 1, what will you write? 1 plus 1 by 1 plus 1. If it is 2x square, if it is x square dx, what will we write? X raised to 2 plus 1 by 2 plus 1 of x raised to 3 by 3. Like that. So if it is n, what will you write? X raised to n plus 1 by n plus 1. This formula we are using now. Another formula, this also we will use later. Integral 1 by x dx log x. Integral sin x dx minus cos x. Integral cos x dx. Integral cos x dx is that is plus. But it is opposite to differentiation. Differentiation, here integral d by dx or sin x, that is cos x plus value. Here it is integration, it is minus value. Opposite you can see. Integral e raised to x dx, e raised to x. This formula you have to remember because coming chapters, we have to use somewhere or other, we have to use these formulas on integration. Only one or two formulas are there. 1, 2, 3. So not only this year, next year also we have to use. So these formulas everybody have to study. Now we are using this formula to integrate the integral x raised to 1 dx. Okay. That formula we are using here to integrate this. See, integral x raised to 0 to x. How we are displacing the spring from 0 to x. X, that is the stretch applied, x. What is the compression? Compression also x. So here, integral 0 to x. X is varying. Kx dx equal to k raised to the formula. We are applying here x raised to 1. We have to consider x raised to 1 into dx. So x raised to 1 plus 1 by 1 plus 1 and give the limit. What is the limit? X equal to 0 to x equal to x. X equal to 0 to x equal to x. So after integration, you see no dx, no integration sign. We just apply the formula. So we have, after applying the formula, no need of putting integration sign and dx sign. Only to put the limit. We have to put the limit here. Lower limit is 0, upper limit is x. That we have to give here. So what is x raised to 1 plus 1? X square. 1 plus 1 again divided by 1 plus 1, 2. That 2 is written here. X square by 2, k into x square by 2, and we give the limit 0 to x. How will you apply this limit? So in the place of x, what is written in the upper part? That you have to write. Here both are x, so no problem. You are writing upper limit x square minus lower limit minus. You can see upper limit minus lower limit x. In the place of x, you give 0, 0 square. What is 0 square? That is 0. So upper limit in the place of x, first give upper limit x, as it both are x, no change, x square itself, minus upper limit minus lower limit. What is lower limit? 0. So 0 square. So we get 0 itself. So half into kx square. This is the way to integrate this expression. So total work done we got by integrating expression, total work done, W. Initially it was dW, small work done. After integration, it changes to capital W, work done, total work done. So the work done is stored in the spring as potential energy. So we find the work done for what? For finding the potential energy of the spring. So what is the potential energy of the spring at the stretched position at B? It is equal to half kx square. Very important derivation. Work done to stretch the spring or work done to compress the spring to a displacement x, that is equal to half kx square, where k is the spring constant of the spring and x is the stretch or compression. Potential, gravitational potential energy we have derived last class. What is it? mgh. That is the gravitational potential energy. This is elastic potential energy of the spring, half kx square. Everybody has to derive and study. Take your notebook, draw the figure, explain the figure, and then do the derivation until you get it. You have to write and study all this derivation. Then next we can see a graph. The variation of potential energy, kinetic energy, and total energy with distance is shown figure. You can see variation of potential energy, kinetic energy, total energy. Total energy means sum of this. With distance, what happened in the case of a spring? What is happening to potential energy, kinetic energy, and total energy? That you can see here. See, A is the original position of the spring. B is the stretched position, C is the compressed position. When we stretch and release, spring will begin to oscillate like this. When we stretch and release, when we apply a force to stretch it, and when we release that force, what will happen? Spring will begin to oscillate. Understand? Like this. So here, stretched position, it contains which energy? Potential energy. Compressed position also potential energy. What is the equation? Half kx. Okay. So here, you can see the graph is explained. Okay. See, at A, x equal to displacement equal to 0. At A means original position, original condition, not stretched position. At A, displacement is 0. Okay. Then what is potential energy? We are not at all doing any work to stretch it. So no potential energy. So work potential energy is 0. So when we stretch and release, what happens? It begins to oscillate. Spring begin to oscillate. So at the extreme position, it will have at C. C is the compressed position. B we have seen maximum potential energy. At C, at B it will have half kx square. At C, what is the potential energy? Potential energy is equal to half k into minus x. To the right we have taken plus x. To the left we take minus x. So potential energy at C equal to half k square itself. You see, but we can draw a potential energy graph. At C, what is the potential energy? At extreme position, maximum. Potential energy is maximum. Yes, this is the curve. Potential energy is not written. Okay. Yes, yes, written. Dotted lines. Dotted lines. So at the extreme position, which energy it is having? Potential energy. At B also, which energy it is having? Potential energy. So this 1 point extreme position. This is 1 point maximum value here. Energy is maximum value. So maximum potential energy here, and at mean position potential energy is 0 because displacement is 0, x is 0, so potential energy is 0. So 3 points we have plotted a graph, and it is a curve half a square. So it is a curve. You are getting a parabola, the upward parabola. So this is the potential energy graph. Dotted line represent the potential energy graph. And you can see kinetic energy graph. And we know during the oscillation, suppose this is the main position, the spring is begin to oscillate like this, it is stretched. So it will have maximum potential energy. And then when it come back, what happens? Potential X is decreasing. So potential energy decreases. And when it at its mean position, it will have the maximum because restoring force. That potential energy is decreasing because of the restoring force. Restoring force is exerting a force towards the mean position. So because of the restoring force, it is coming back to the mean position, but it cannot stop at the mean position. It will move to the left extreme due to inertia. It move to the right extreme, but again restoring force pull it to the mean position. Like that, the spring begins to oscillate between the mean position and the extreme position. So at the mean position, do you know which energy it will have during its oscillation? Anyone tell? During the oscillation, which is the maximum kinetic energy or potential energy? Please tell. Children, please tell. Anyone can tell. During its oscillation, at the mean position, the spring is oscillating. During its oscillation at mean position, it will have which energy? Potential energy or kinetic energy? Maximum. Nobody is answering. Why like this? Then I'll call. Okay. Anushankar. Anushankar. Are you there? No.
I don't know, teacher.
You don't know? Just I'll explain once more, then you will tell. See, at A is the mean position of the spring. Okay. Listen. Don't know tell is very easy, but you know you understand the things, and I will.
I missed a lot of class, so I didn't understand actually.
What?
I missed a lot of class. This is my first class in this chapter.
So what? I am explaining this phenomenon now. Okay. You just listen. Under that feeling, don't sit. So you just listen what I am telling now and try to answer. Okay, I will explain. So the spring, there is the mean position of the spring. And when we stretch it, what happens? We are doing work to stretch the spring. And that work done will be stored as potential energy, elastic potential energy. Okay. So in the stretched position, which energy it will have? Manu?
Potential energy.
Potential energy. Okay. And suppose we after stretching it, we release it. We removed our force. The spring will begin to oscillate. Here it is resting on a horizontal surface, so it will begin to oscillate like this, about the mean position. It will oscillate, move to the right to a distance x, then to the left to a distance x. Sometimes it may be less because of friction. So like that, it begins to oscillate. So at the expression for potential energy is what we derived, half kx square. That is the expression. So x decreases, what happens? Potential energy
Decreases.
decreases. Potential energy decreases. So automatically at mean position, what is the potential energy? Mean position?
Less.
What is the
It will
potential?
be less. It will be less, right?
Less means x is 0. So what is its value?
Ah,
What is its value? At mean
0.
position, 0. Potential energy 0. Okay. So at the mean position, potential energy becomes 0 because x equal to 0. Clear?
Ah,
Okay.
yes.
Okay. Extreme position, which energy it will have? Extreme position, that means to the left extreme, compressed. It is oscillating.
Ah,
At C,
ah,
which energy is maximum?
ah.
Kinetic energy, potential energy. Half kx square is there, no? Half k into minus x square. So potential energy is maximum. And see, you have to think about the oscillation of the spring. So the spring is oscillating about the mean position, the right extreme position, potential energy maximum. Then why it come back? Do you think when we release our force, why it is coming back? Do you know why it is coming back? Which force is acting on it? Why the spring come back? Tell. Which force is acting on it to bring it to the mean position?
Kinetic.
Which kinetic is energy, no, not force. Which force is bringing it to the main position?
Restoring force.
Which force?
Restoring.
Restoring force ആണ്. Restoring force is bringing it to the mean position. അപ്പൊ നമ്മളിപ്പോ ഒരു ബോഡി മുകളിലേക്ക് എറിഞ്ഞു കഴിഞ്ഞാല് അത് കുറെ ദൂരം പോയി കഴിഞ്ഞിട്ട് താഴ്ത്തേക്ക് വരുന്നില്ലേ? അതെന്തുകൊണ്ടാ? ഗ്രാവിറ്റേഷണൽ ഫോഴ്സ് ആക്ട് ചെയ്യുന്നുണ്ടല്ലേ? അപ്പൊ വെലോസിറ്റി 0 ആയിട്ടാണ് അത് തിരിച്ചു വരുന്നത്. അപ്പൊ എക്സ്ട്രീം പൊസിഷനിൽ എത്തുമ്പോ വെലോസിറ്റി 0 ആവുന്നത് കൊണ്ടാണ് അത് തിരിച്ചു വരുന്നത്. ബിക്കോസ് അതിനെ ഇങ്ങോട്ട് വലിച്ചുകൊണ്ടിരിക്കുകയാണ്, റെസ്റ്റോറിംഗ് ഫോഴ്സ് വലിച്ചുകൊണ്ടിരിക്കുകയാണ് ഇങ്ങോട്ട് ഓപ്പോസിറ്റ്. നമ്മൾ സ്ട്രെച്ച് ചെയ്യുമ്പോ അതിന് ഓപ്പോസിറ്റ് ആയിട്ട് റെസ്റ്റോറിംഗ് ഫോഴ്സ് അതിനെ ഇങ്ങോട്ട് പിടിച്ച് വലിച്ചുകൊണ്ടിരിക്കുക. അപ്പൊ അതിന്റെ വെലോസിറ്റി 0 ആവും. നമ്മൾ ഫോഴ്സ് റിമൂവ് ചെയ്യുമ്പോൾ എന്തായാലും പെട്ടെന്ന് അത് തിരിച്ചു വരും. പക്ഷെ അതിന് സെന്ററിൽ എത്തുമ്പോൾ സ്റ്റോപ്പ് ചെയ്യാൻ പറ്റില്ല. Because of inertia, it moved to the left extreme. Again, restoring force pull it back to the mean position. So velocity becomes 0 and it comes to the mean position. So at the extreme position, velocity is becoming Mitra, what is happening to velocity at extreme position? Mitra? What is happening to velocity at extreme position?
It becomes 0.
Velocity becomes 0. Why you joined late today?
So I was having a problem.
Okay. So at extreme position, it is velocity becomes 0. So kinetic energy is 0 at the extreme position. Potential energy is maximum. In between, you can see when it coming back, x is decreasing, potential energy decreases. At the same time, kinetic energy increases. And at mean position, kinetic energy is maximum. Then it moved to the right extreme, x is increasing, the potential energy is increasing. And at the extreme position, potential energy maximum. Then velocity is 0 because of restoring force. It is pulling it back to the mean position. Velocity is 0. Okay. So extreme position, kinetic energy becomes 0. Where is maximum kinetic energy? At the main position. Now I will ask question. Okay, the reader. Please answer. Don't sit without answering. Okay. Tamanna Biliraj, tell at extreme position which energy to have? Kinetic or potential maximum? Extreme position. Tamanna. Krishna Prabhatal at extreme position, which energy?
Yes, ma'am.
At extreme position, which energy it has?
Potential energy.
Maximum. At mean position, it has maximum?
Kinetic energy.
Kinetic energy. Okay, correct answer. So in between it will have both the energies. Understand? Kinetic energy decreases, but potential energy increases. Like that. But some of the energy become constant. Some of the energy become constant. Okay. That is a graph showing. You see, potential energy we have plotted and kinetic energy, that green color parabola, that is the graph for kinetic energy. Ke is written kinetic energy. At extreme position, kinetic energy 0. This see at extreme positions are marked C and B. And extreme position energy is marked along the y direction. So here it is along the same line means 0. Kinetic energy is 0 at the extreme position. So you have to mark 2 points here. But kinetic energy is maximum at the mean position. That means original position A. Kinetic energy is maximum. So join those 3 points. We get a parabola. We don't join with a straight line because as per the equation it is half kx square. So we get a parabola only, not a straight line. So we get a curve for potential energy, the dotted lines, and that green color parabola downwards, that is representing kinetic energy graph. And you know, in between it will have both the energies. So when you add this at this position C, it is having maximum potential energy, minimum kinetic energy, and total energy. When you add, we get a constant. Total energy will be constant. In between its motion, total energy is found to be a constant. Understand? If at extreme position it is having maximum potential energy, but 0 kinetic energy. But total will be same, half kx square itself, it will be total, will be same. So that is explained here. Half k at extreme position C, potential energy is equal to half k into x square. So this graph also is important. Kinetic energy is converted into potential energy of the spring. This is repeated. The body oscillates about the equilibrium position A between the position B and C. Total energy in all positions remains the same. That is an important point. If m is the maximum speed and xm is the maximum displacement, then half mv square, that is the kinetic energy, maximum kinetic energy, is converted into maximum potential energy at the extreme position. Maximum kinetic energy at the mean position is converted into maximum potential energy at the extreme position. So we can write this equation half mv square. Vm is written, it is maximum, equal to half k into xm square. Xm means what? Maximum displacement, extreme position, xm square. They are equal. Potential energy is maximum, kinetic energy is 0. And kinetic energy is maximum, potential energy is 0. So you can equate that. Therefore, we can find out the maximum velocity. We can find out Vm equal to square root of k by m into xm. Square root of k by m. See this m come here. Half get cancelled. So Vm square is this, and Vm will be square root of k by m into xm in the square, the root to the xm. Square root of k by m into xm. Xm means what? Maximum displacement. X suffix m, suffix. Not m like this. ഇതുപോലുള്ള m ആണ് എഴുതിയിരിക്കരുത്. X താഴെയാണ് m എഴുതിയിരിക്കുന്നത്. xm suffix ആയിട്ട് എഴുതണം. xm means maximum displacement. Okay. Can you take down the notes? Be careful. Only 5 minutes more. How much time we are taking? You see, only one derivation. Last day, 5 minutes only more. So we have to take extra classes. So we have plotted the graph. Next, mechanical energy and its conservation. Mechanical energy means what? It is the sum of potential energy and kinetic energy. What is mechanical energy? Sum of kinetic energy and potential energy. K means kinetic energy. V means potential energy. Sum of these two, that's the total energy. That is known as mechanical energy. Next, what we have to study? Mechanical energy and its conservation. That is what we have to study. The total mechanical energy of a system is conserved if the forces doing work on it are conservative. We know gravitational force is a conservative force. What is a conservative force? Work done by or against the force depends only on the initial and final position, not on the nature of the path followed. Such a force is conservative force. A gravitational force is a conservative force. So here we have to show the conservation of mechanical energy. This example. This is the example. You can see a body is lifted at a height h from the ground level. This is the ground level and body is at a height h. Body is at a height h. Then it is released. The body is released from a height h. What will happen? At a height h, what is the potential energy? mgh. When it is released, what is happening to potential energy? I'll ask to Abarna. Abarna, are you there? When it falls downwards, what is happening to potential energy? Decrease or increase? Abarna. Answer.
Decrease, ma'am.
Decrease. What is the formula for potential energy?
MGH.
mgh, correct. So h decreases, potential energy decreases. At the same time, what is happening to kinetic energy?
Increases.
Increases. Yes, correct answer. Because when a body falls downwards, velocity increases. So half mv square, velocity is increasing. In between, it will have both the energies. At extreme position, it is having maximum. See, it is at a height h, not moving. Initially, body is at a height HA, at the position A. It is at rest. So kinetic energy is 0. Then it is released. Then it is dropped. That body is dropped. So as H decreases, potential energy decreases. And what happened to kinetic energy? Kinetic energy increases. Because we all know when a body falls downwards, velocity increases. That we have studied. So in between, it will have both the energies, but just before it hit the ground, what is the potential energy? It will last to Lakshmi Priya. Just before it hit the ground, which energy it will have? Kinetic energy or potential energy? Maximum. What? Which energy? Kinetic energy. Correct, sir. So just before hit the ground, H is almost 0. So it will have potential energy 0, but it will have maximum kinetic energy. Correct answer. So we have to show that at all position, at A, at B, we have taken intermediate position B, and we have taken the just before it hit the ground C. All these positions, the total energy is constant. That is what we have to show that. So here at A, we told potential energy is maximum mgh. At A, mgh. Kinetic energy is 0 because it is held at A. Held at A means no motion. It is held at A, so motion is not there. So kinetic energy is 0. Kinetic energy of the body is 0. Potential energy is mgh. Therefore, total energy is 0 plus mgh. So we get total energy is mgh. Similarly, at another position,